morning, everyone. This should be our last narrated notes for chapter 9 because dilations 9-6 is the last thing that we're going to be doing. So dilations are the only examples of transformations that we have that are non-rigid motion because the size does change. So the figures end up being similar because they still maintain the same shape. All the angle measures would stay the same, but the image is either going to get smaller or larger. So we know it as zooming in, zooming out. The content of what you're actually looking at doesn't really change, the composition of it, but it just gets bigger or smaller. So the scale factor is just a comparison between the pre-image and the image. So if the scale factor is greater than 1, you would have an enlargement. If the scale factor is less than 1, you would have a reduction. So here are just a couple of examples of dilating when the origin is the center of dilation. So it just means that all of this is happening sort of around the origin. And these are actually pretty easy. So my original figure, again, was in the white, this quadrilateral here, and my directions were to dilate by a scale factor of 1/2. So it's really pretty simple. I just took all of the original points and plotted where they were, and then I'm just going to multiply every coordinate by the scale factor. So half of -1 is -1/2, half of 2 is 1, etc., etc. Down here, half of -5 is -2.5, and half of -3 is 1.5. Once I have my new coordinate points, after multiplying by the scale factor, I just plot those new points. And there I have it, my reduction. Here I'm dilating by a scale factor of 2. It works exactly the same way, except this time I'm multiplying all the coordinate points by 2. So I plotted out my original figure, got the coordinate points, then multiplied everything by 2. -5 times 2 is -10, -4 times 2 is -8, and so on and so forth, and then I plot those new points. And again, at least visually, I could see that these are reasonable because, again, it just looks right. If you dilated these figures and somehow your shape didn't look similar, you would know that you did something wrong. And honestly, the thing that people are going to do wrong more than anything else is just plot the original points incorrectly, count incorrectly on the coordinate grid, and then everything gets thrown off. But you should just kind of take a look at it at the end and make sure that it still at least has that look of similar figures. Same shape, just different size. So again, when the center of dilation is 0, 0, the origin, it's pretty easy. What's a little bit more complicated is dilating from a point that is not the origin. This is a lot more challenging. And again, I don't think you're really going to have to do a lot of these as much as you're going to have to recognize them. And since we don't know what's going on with the state test, you might not ever need it at all, but at least here it is. So what I have to do first is, here my direction is dilate by a scale factor of 2 from the center of dilation, point Z, which is -3, -2. Sorry, I wrote these directions before I actually did my dilation. That's why it went too far. So anyway, the first thing I'm going to do is count the slope from the point of dilation to each point on the original figure. So I'm just labeling everything that I'm kind of doing. I'm going to count from Z to S, then I'm going to count from Z to J, and then I'm going to count from Z to A. And I'm just going to remember that slope is rise over run. So if I'm going from Z to S, 1, 2, 3, 1, 2, 3. So I'm writing this 3 over 3. I'm not reducing it. I'm leaving it like that. Then ZJ, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. ZA, 1, 1, 2, 3, 4, 5. So I have my original slopes. What I'm going to do next is multiply all numbers by the scale factor. So since my scale factor is 2, I'm multiplying everything by 2. So 3 over 3 becomes 6 over 6. Again, that's the little tweak. I'm not multiplying it by 2 over 1. I'm multiplying every number by 2. Then since ZJ was 4 over 6, once I multiply both of those numbers by 2, I get 8 over 12. And then ZA was 1/5. Once I multiply those numbers by 2, I get 2/10. An interesting point here, you can see right here where I had to scratch out a number and fix it. This is one of those where I had counted this incorrectly, and I realized that I counted it incorrectly when I went to plot my new figure, and I had a horizontal line. And I went to myself, but I don't have a horizontal line in this figure. Why am I getting a horizontal line in this figure? And that prompted me to recount. So again, sometimes you're just going on the idea like, wait, something doesn't look quite right. And that's your prompt to go back and look at something. So once I've done all my multiplication here and I get my new slope that reflects the multiplication by the scale factor, I just recount from the point of dilation with the new slope. So now ZS should be 6 over 6. So I start at Z, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And there's my new S. Then ZJ, that should be 8 over 12. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's how I got all the way over there. And then ZA is 2 over 10. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have my new points, I connect them all, and there's my new figure. So that is how to dilate from a center of dilation that is not the origin. Now, if I had to find the center of dilation, I would need a ruler, so I'm going to go get one real quick. Talk amongst yourselves. Okay. If I had to find the center of dilation, what I would have is I would have two figures already drawn. And what I would do is I would look at the 2 points, the 2 matching points, my S1 and my S, and I would draw a line, and I would try to draw it really long because right now I'm pretending that I don't know where the center of dilation is. I would connect these 2 points. Then I would connect my J's, and I would make a really long line there. And then I would connect my A's, and I would make a really long line there. I would have 3 lines that connect in a point that would all intersect. That's my center of dilation. So again, it's all about you go forwards to do the transformation and you kind of undo it sometimes to find the rule or the point where you would have started. The scale factor is simply, if you had to find one, you would pick 2 corresponding sides, find the length, and ask yourself what happened. So if I had a figure, let's see, over here, it works a little just easier to explain on this horizontal line. If this PO is 1, 2, 3, 4, 5, 6, 7, 8, 9 units long, and this, again, I'm starting at a half a unit right here, 1, 2, 3, 4 and a half. PO was 9. P prime O prime was 4.5. So then I ask myself, what's the relationship between those 2 numbers? Well, I could think about it 2 ways. 2 times 4.5 is 9. 4.5 is half of 9. So I'm thinking my choice right now is 2 or 1/2. Then I just ask myself, well, what actually happened? Well, since my original figure was bigger than my transformed figure, it got smaller, I would know that my scale factor has to be less than 1. That's how I would understand that my scale factor is 1/2. So if you have to find a scale factor, just do so by finding the lengths of 2 corresponding sides and then finding the relationship between those 2 sides. And then again, on a coordinate grid, if you have a horizontal or a vertical line, you can just count units, but if you have a diagonal line, you have to use the distance formula. Again, that's probably more than you're going to have to do for this unit, especially this side over here. dilating from a center that's not the origin, but at least you have the information if you need it, and it's at least background if it comes up. So that is the end of my notes for chapter 9, and I'll see you in the next chapter.